In the vast world of electronics, where intricate circuits power our modern lives, soldering stands as an indispensable process. It is the invisible force that binds components together, enabling the flow of electricity and information. From smartphones to spacecraft, soldering plays a crucial role in countless technologies we rely upon every day. At the heart of this essential process lies soldering lead, a material that has long been synonymous with the art of joining metals. Soldering lead, in its various forms and compositions, has enabled the creation of complex electronic devices, intricate jewelry, and durable plumbing systems. However, as our understanding of material science and environmental impact has grown, so too has our need to explore safer and more sustainable alternatives. This essay delves into the fascinating world of soldering lead, unraveling its dual nature as both a material and a wire. We will explore the history of soldering lead, its composition, and its diverse applications across industries. Furthermore, we will examine the reasons behind the shift towards lead-free alternatives, highlighting their benefits for human health and the environment. Join us on this enlightening journey as we uncover the secrets of soldering lead and its evolving role in our technological landscape. Soldering lead, often referred to simply as solder, can be a bit confusing because it's used in two different ways. First, lead is a key ingredient in the. Second, we use the word lead to describe the that's made from solder. Let's untangle this. When we talk about lead as in solder, we're talking about a soft, silvery metal that's been used for this purpose for centuries. When lead is combined with tin, it forms an alloy that melts easily at a relatively low temperature. This makes it ideal for joining metal components without damaging them. Now, let's talk about solder wire. This is simply a thin wire made from the lead-based or lead-free solder alloy. It comes wound on a spool and is heated up with a soldering iron to melt it and make the electrical connections. The type of solder wire you choose will depend on what you're soldering and whether you need a lead-based or lead-free option. Why are there alternatives to lead-based solder? Well, as useful as lead is, it's also toxic. Exposure to lead can cause various health problems, especially for young children. That's why there's been a global push to reduce lead exposure, and one way to do that is by using lead-free solder. Lead-based solder, as its name suggests, contains lead as its primary component. The most common type of lead-based solder is a tin lead alloy, typically containing 60% tin and 40% lead, known as 60-40 solder. This specific composition offers an excellent balance of properties, including a low melting point, good wetting ability, and strong mechanical strength. The applications of lead-based solder are vast and varied. In electronics, it is widely used for soldering components onto printed circuit boards, PCBs, the backbone of countless electronic devices. The low melting point of lead-based solder prevents damage to sensitive electronic components during soldering. Beyond electronics, lead-based solder finds applications in plumbing, where it is used to create watertight seals in pipes and fittings. Its corrosion resistance makes it suitable for use in plumbing systems carrying hot and cold water. It's important to note that using lead-based solder in plumbing is now restricted in many countries due to health concerns. Another notable application of lead-based solder is in stained glass work, where it is used to join pieces of colored glass together. The low melting point of lead-based solder allows artists to create intricate designs without cracking the glass. However, even in art, there is a growing trend towards lead-free options to minimize exposure to this toxic metal. As awareness of lead's toxicity grew, so did the need for safer alternatives, especially in applications where human exposure is a concern. In 2006, the European Union implemented the Restriction of Hazardous Substances Directive, which effectively banned the use of lead in many electronics. This landmark legislation sparked a global shift towards lead-free soldering, driven by both health and environmental considerations. Lead exposure can have detrimental effects on human health, particularly in children. It can lead to developmental problems, learning disabilities, and even damage to the nervous system. Pregnant women exposed to lead face an increased risk of premature birth and low birth weight in their babies. Furthermore, lead is a persistent pollutant that accumulates in the environment. When electronics containing lead end up in landfills, the toxic metal can leach into the soil and water, contaminating ecosystems and potentially harming wildlife. The move towards lead-free solder is a crucial step towards mitigating these risks and protecting both human health and the environment. By transitioning to safer alternatives, we can reduce lead exposure and minimize its impact on our planet. The search for lead-free alternatives has led to the development of a variety of solder compositions, each with its own unique properties and applications. One of the most common lead-free solder alloys is tin copper, often with the addition of silver to improve its properties, known as SARC solder. Tin copper solder offers a higher melting point compared to lead-based solder, making it suitable for applications where higher operating temperatures are required. It also exhibits good mechanical strength and wetting characteristics. Another popular lead-free option is tin silver copper or SAC solder, which offers a lower melting point than tin copper solder while maintaining good mechanical properties. SAC solder is often preferred for electronics assembly due to its lower melting temperature, which minimizes the risk of heat damage to sensitive components. Other lead-free solder alloys include tin zinc, tin bismuth, and indium-based solders. Each of these alloys has its own set of advantages and disadvantages, making them suitable for specific applications. For instance, tin zinc solder is often used in plumbing applications due to its good corrosion resistance, while indium-based solders find use in specialized applications like cryogenics due to their low melting points. The journey of soldering led from a ubiquitous material to one facing increasing scrutiny reflects a broader trend in material science and manufacturing. As our understanding of the long-term impacts of materials on human health and the environment grows, so too does our responsibility to seek out safer and more sustainable alternatives. The shift from lead-based to lead-free solder is a prime example of this evolving mindset. While lead-based solder continues to offer advantages in certain applications, the health and environmental concerns associated with lead necessitate a move towards safer alternatives. The development and adoption of lead-free solder alloys demonstrate our ability to innovate and create materials that meet both performance requirements and sustainability goals. As technology advances, we can expect to see further advancements in lead-free solder technology, leading to even safer and more environmentally friendly soldering processes. The future of soldering lies in striking a balance between performance and sustainability. By embracing lead-free alternatives and continuing to innovate in material science, we can create a future where electronic devices are not only powerful and reliable, but also safe for both people and the planet.